I just handed out the homework number 2. This homework set is directly related with the materials we are discussing. Actually, section 10 is very important for you to solve this problem and to get ready for the upcoming midterm test. This homework number 2 is relatively simple. We have LLC inverter. Okay, the parameter of this inverter is very similar to those of our design example. So we covered the design of the tank circuit. We are covering the design of tank circuit, and this problem concerns with the analysis of tank circuit. So maybe the reverse direction of the discussions we are having here, right? Okay, and my plan is the midterm test will be the design problem, tank design problem, very similar to the inverter we are discussing now. Okay, so section 10 is very important. I think at least the student should know section 10. Okay, that is the key of the formal part of this semester. Okay, all right. Okay, so we first finish up the last part of section 10, which is validation of design, relatively easy, because we designed everything. In particular, we found out this H infinity and the G, O0. So with those values, these values can be directly calculated using the simple formula. So this is the result of the open circuit voltage measured at this port, not this one, here at the output of inverter, and the short circuit current, and we designed them. This is the design value. So we have this, and R critical is seen here. Okay, this one is R critical seen at this node, but we need to know this R critical seen at the output of this inverter, and this is just numerical calculation. And during the design process, somehow we targeted this value to be 5. This was one design option. Okay, so we select ratio of this thing to be 5 to get some efficiency improvement at line node condition. Okay, so this is the design result, and the maximum power here is, we know this value, open circuit voltage and the short circuit current, then P max. Maximum deliverable power using this tank circuit is this one, square root 2, and we already have RMS value here. So just a simple calculation of this is 32 watt. Our rated power was 20 watt or 25 watt. Okay, so we have some margin. All right, so this is a reasonable design, and the input impedance characteristics seen at the input port of the tank circuit. You know this. This is one curve, GI infinity, and another curve, GI 0. Okay, and this frequency is this one, is resonance between C and LS, and this is this is the resonance between C and LS plus LP, and this is resonance between C and LS, right? So we have some difference, and this is the frequency which all the input impedance curve merge together and pass through the other region through this pinhole. Okay, so I evaluate this one at this frequency, at the switching frequency. Switching frequency is 100 kilohertz. Okay, so you may plot this. You may plot the whole curve and just take a look at this point, or you evaluate this one. This is very easy to evaluate because we have 3 reactive components and 1 resistor So you have one C, this is the LSC, and LP, and we have effective RE, but this is shorted. Then input impedance of with this one shorted is series connection of this, and with this become infinity is the series connection of three reactive component. So you can easily evaluate magnitude of this, taking the real part and imagined part, and taking the square root of each terms. Right? So you need to calculate this. So for example, at this switching frequency, open circuit tank current can be measured. This is the tank voltage, first harmonic component of tank voltage. This is the magnitude of this one, GI infinity. Evaluate at this frequency. This can be simulated or calculated. Then this is this open circuit tank current is 2.2 M. This is peak value. And similarly, the short circuit tank current is evaluated like this. All right. So we have the difference between this is about 3 times. 3 times. All right. So this number 3 is somehow related our design target in the previous lecture slide. During the design process, we select this number to be 5. Okay. Then this number should be 5 because that is directly related with this magnitude remain the same, only this one is changing. So you have 3 times difference here, about 3 times difference here, and we have about 3 times difference here. Okay. So we selected 5, but somehow we modified, we selected this reactive component using some other constraint. So we targeted 5. The final result is 3. Okay. But this is good. This is good enough. Okay. Because there are 2 other design freedoms, and by using that, somehow that their ratio is reduced from 5 to 3, but that is still okay. Right? So this means this is short circuit current, and this is the open circuit current. So this should be large and this should be small, right? Because we have this type of input impedance characteristics. If we select the switching frequency somewhere here, then this direction will be opposite, which is very bad. Okay, so you have a good result. Okay, so from here maybe you can expect, we hope the line load efficiency will be good or reasonable line load efficiency is expected somehow. Okay, and this is the inverter ellipse. This is very, very important. So we calculate this, and we know this R match. Oh, something is missing here. We are seeing everything at the output side, so N squared is necessary here, and R critical is calculated as 400 ohm, and the R is the R we are using. Okay, and equation for the R critical is we need N squared because you are seeing R critical at the output port, and inside of tank network we calculate this number. You don't have to be scared of seeing this symbol. Okay, symbol is complicated, but meaning is extremely simple. Just to evaluating the magnitude of some complex number. That's it, right? So, and you have GBS, R, larger than R critical. So this is the GBS region, and our normal R is here. So with this R of 500 ohm, you have GBS, but margin is very small. Okay, phase delay will be small, relatively small, because difference between 400 and 500 is just 20%. It's not big difference. simulation result. This is a PC model. Maybe in the midterm test, you may need something similar to this. All right. So you need to simulate something using this type of PC model, which is very trivial. Okay. This will determine the switching frequency, and it's very easy. Finally, simulation result. So you are watching 4 waveforms. First one is this one, IT1, tank current, and this is tank voltage VT, and this is output voltage, sinusoidal waveform, and load current, sinusoidal waveform. I should put here, right? Because same thing. No. The input impedance V is 0, so I don't know. This might be okay. Okay. So VT is this one, 12 volt, minus 12 volt. Okay. So it's pulse waveform, and IT1 is this one, sinusoidal waveform. Okay. Not exactly, but very similar to the sinusoidal waveform. And this peak value of tank current is evaluated simply by dividing the peak value of this one, first harmonic component of this one, divided by GI. GI evaluate at 100 kilohertz. Evaluate at 100 kilohertz and R of 500 ohm. Okay. Just calculate this number or simulate this number and calculate this and put this number here. Okay, you may do this and compare with this number. And this one, top value of this, they should be very similar. Right? And this is the output voltage magnitude. As this one, this is target value. So this is very close to this 100 something. 141 something. Okay? And this tank current, magnitude of tank current is this one. This is our target, and this value is very similar to our target. Okay? They are fairly different from the sinusoidal waveforms, but the peak value somehow they closely match our prediction, assuming that everything is sinusoidal wave. Right? And the P maximum power, power at this point, you multiply this one with this one, and they are peak value, so you need this factor of 2 is about 21. Okay, so desired power was rated power was 21. Okay, so this is the end of section 10, and this will be a good review of the technical content covered in section 10. All right. Okay. So we move next one. No, 11. This topic is very easy. So this lecture may be some entertaining class for you. Okay. So you don't have to pay too much attention on this, right? But this is just reviewing everything and summarizing all the technical discussions we went through in section 10. All right. So topic of this is an ultra low profile series resonant converter. I posted 2 reference papers on this topic. One is about this one, and the other one is the connectionless charging circuit for the cellular phones. All right. So that might be good to review everything. So if you have some time, just take a look at those references. All right. So this is our discussion start here. Okay. This is the photo of experimental series resonant converter. This is the converter, right? So this is built on the double-sided PCB. So this is the top view, and this one is bottom view. So it is double-sided PCB, and one is you are looking from the top, and one is looking from the bottom. So this is the same thing. Right? So one with different viewpoint. Okay, and this is the spiral winding. This is spiral winding, and this is the other side of spiral winding. This black one is covered in both sides, but I just take out to show inside of this. This is ferrite FPC, ferrite polymer composite tape. This is the magnetic material, but it looks like just the tape, okay, sticky tape, right? There is some kind of core material. So I used this to shield the magnetic flux generated through this coupled winding, right? So this was necessary for the magnetic shielding. So at that time, I saw this, and I contact the company in the United States, and I get some free samples, and I used the samples to cover this one. Okay, so this is the one side of spiral winding, and it is the other side of spiral winding. All right. So this is the connection. So I made something very small, like the bridge. So it's connecting from this center part of spiral winding to this. Okay. The other part is somewhere here. The other end point is somewhere here. Right. So this is used as the energy transfer device with electrical isolation in between. This is the circuitry. Right. So we try to use very small devices, but somehow this chip is still large. This MOSFET is still large. This is the not current transformer, pulse transformer for the gate drive circuit. Okay, and this is the size of this converter. So this is the 8 centimeter. I thought this is 6 centimeter, but I found this was 8 centimeter. Okay, but this can be reduced. All right, with some other devices, this can be reduced, and power transferring part is only this part. Okay, so input voltage of this converter was this 40 to 60. Output voltage was 24, and this output current. So maximum power was about 60 watt, and the average efficiency was 80%. Okay, and dimension is this. This is the length, width, and the height. Okay, height is taken from this one, this gate, this MOSFET switches, and some ICs. All right. So we'll go through all the details about implementation of this, and we'll use or review our previous analysis about the circuit behavior of this converter. This is a simplified schematic diagram of converter. So it looks like this. All right. So this is the spiral winding built on the double-sided PCB. Looks like this. So this is one spiral winding, and the other spiral winding is the other side of this double-sided PCB. And we have only one capacitor in the tank circuit, and we are using this one, leakage inductance and the magnetizing inductance of this. Okay, and this is definition of the dot. Okay, this is coupled inductor, so we need to have this dot convention. This dot means if the current is entering through the terminal with dot, suppose one current is passing through this direction, and the other current is also entering to the dotted terminal of winding, then the flux generated with those two windings are mutually additive. All right? If one is generating this direction and the other one is magnetic flux generated current entering this dotted terminal should be same direction as the previous one. There is the definition of this dot convention. Right? So this is dot convention, and eventually, first we model this as the coupled inductors, and later on we modify that model into this structure. This structure is circuit model of conventional transformer. So you may consider this as a transformer with specially generate LK and LM and this coupling ratio, turns ratio. So this coupled this spiral windings, they are identical, but this turns ratio is not 1:1. It's 1:8. A is some number different from the 1, right? Because this structure is not symmetrical. If everything is symmetrical, they should be 1:1. But all the parameters appearing only in the left side of this ideal transformer, so this should be different from the 1. If that is 1:1, that guy is lying. Okay? So, all right. And this is waveform. This is a series resonant converter waveforms. So this is tank voltage. This is a pulse waveform, and it's a fundamental component of this rectangular waveform. And this tank current, which is sinusoidal wave, because we have very high Q filter here. So only this tank is responding only this component. So you have this sinusoidal tank current with some phase delay. Okay, so we have GBS characteristic here, and this is the waveform, voltage waveform here. Here, okay, VR2. This voltage is sinusoidal, right? This should be no. This voltage. This okay. I'm sorry. This is current. This current is sinusoidal, all right? So from this structure, it looks like the parallel loaded, but I told you several times there is some leakage component originally coming from this side. Originally it was here, that was deflected here. Right? So this is a series resonant circuit. So one current entering path and one current leaving path. This is a series resonant tank. So this current is sinusoidal and this current is also sinusoidal, but there is a phase difference in between. So this primary side tank current, I should use number 1 here, IT1, meaning this tank current is almost sinusoidal wave of fundamental frequency, and this IR1, but phase delay here and phase delay here should be different, right? Because we have something in between, this L, so it provides some additional phase delay. This waveforms seen primary side of this coupled windings, and this is waveform seen at the secondary side of this coupled windings. So this is IR here, which is basically the fundamental component. Okay, so this we assume this is purely sinusoidal, and this current is rectified. This current is rectified. So IR1 is like this. And the AC current of this part is entirely passing through this capacitor. So only DC component of this current is passing through this R, load resistor. So VO is just the voltage drop across this R due to this DC current, so which is this. Okay, so this works as the voltage source. When these two diodes are connected, this one and this one and this one are connected, this positive voltage is appearing across this node. So we have, this is wrong. This was a mistake. It should be out of phase. Original one was a mistake. Okay, so it should be something like this. All right, so this is wrong. So this current, this IR, and this VR is always in phase because you have this diode rectifier. They should be in phase all the time. So you have this, and this is the circuit waveforms. And later on, we'll compare prediction of this and the waveforms measured from the hardware. Right? So there is one big difference compared with the content of section 10. Section 10, we design tank circuit. Okay, here this tank circuit is given by this. If you made this structure of this, if you fabricate this, double-sided PCB winding, closely coupled, then there is not much room to control these parameters, right? So these values are already fixed. So for the given tank parameters, you wisely select the switching frequency and everything. So this situation is different from the previous one. Okay, there is no design procedure here. Probably you slightly modify these values by changing these windings and the thickness of this, but that room is very narrow. Okay, everything is given. This situation is very similar. The situation they are having in the industries. Okay, for the low profile design, they squeeze everything into this narrow height. Okay, they have planar type of transformer and size is limited. So they try the very dense transformer and measure the values of this, and they select the switching frequencies to provide the good operational region for this converter. Okay, so they don't have a design procedure actually, but to have a proper operation, they should understand everything, including the design process. So for the engineers working on this area, they should understand all the story we are covering, everything about this, GCS, GBS, arc critical, and what this ellipse. Okay, based on that, if they understand everything, so they know how to play with this for the given this structure or given the transformer is already given. Maybe they order to some manufacturers. Okay, they just take that transformer and they design the circuit. Right, just select this resonant capacitor and select switching frequency and the operating region. Right. Okay, so this is different from the design, but everything is given by some physical dimensions of this PCB winding structure, right? Okay, so this is the operational condition. We went through this, right? So this is the result. Our power was about 60 watt, and the maximum efficiency is about 90%, and nominal efficiency was 85%. And power stage component, this is the MOSFET, maybe with very small RDS on. I don't know what type of MOSFET I used. It was built maybe more than 15 years ago. Okay, this is the film capacitor, and this is MLCC, right? Very low ESR and Schottky. This is the control IC for the resonant converter, and this is the compensation structure. I use simple integrator. This is the worst compensation to use, but at that time we just check the closed loop regulation and the stability of converter. So we didn't pay much attention on this. We just select this. This is working, okay? But this can be improved. Right? Actually, the later part of this lecture will focus on the designing of this one. Okay, maybe this is the worst selection. Okay, always, I'm saying always this integrator is the worst compensation. It only provides DC regulation, and it hurts the stability margin and other closed loop performance badly. Okay, so this is the just one example. So maybe if I select other structure, transient response, this will be improved. But our interest was just showing this, okay? Functionality of this. This is the structure of PCB winding. This is the side view. This is the PCB laminate, bakelite laminate, and this winding, copper winding, right? Spiral winding. And this is the FPC sheet, okay? The black one. We used this for the magnetic shielding, okay? I don't know the details about this. I just searched And I contact the company and ask for sample sheet, and they provide this ferrite polymer. Maybe relative permeability is relatively small, this one. Less than 1,000, something, I don't know. Less than 1,000, something like that. This was necessary for the magnetic shielding. Right, and these are dimensions. Thickness of trace was important, right? Because the switching frequency is about 1 megahertz. The skin effect was the issue, right? So to minimize the skin effect, this thickness should be thick, relatively thick. So we used this one, 3 ohms for feet squared, and this is thickness of PCB laminate, thickness of FPC sheet, and so on. Okay. We didn't design this. We just made this spiral winding, trial and error, and we used whatever we have. Okay. So this is the backward engineering. Then we needed to measure everything about this. This is a double-sided PCB and 2 spiral winding. I explained how this dot is placed. All right. So we used this coupled inductor model. Right. So coupled inductor model is not a transformer model. This coupled inductor model is very general that can apply to any two-port networks. Okay. So here we have these windings, but actually it really does not matter what you have inside here. All right. Just circuit behavior of this two-port network is modeled as this one. This one is not an inductor. This one is something mathematical called coupled inductor. So it just obeys this equation, right? It's not a winding. It's not an inductor. It's just a symbol, like the ideal transformer symbol. But this model is satisfying this equation, and these parameters L1, L2, and M has the name L1, L2 are L1, L2. Okay, L1, L2 are self-inductance, and this M is mutual inductance, all right? And the nature of mutual inductance is just, it obeys, it follows this equation. With this, if you know this L1 and L2 and M, then you assume this equation, this device is satisfying this equation if you properly identify the 3 parameters, L1, L2, and M, 2 self-inductances and 1 mutual inductances, right? So this is a very general model. Any two-port network can be modeled in this manner. Maybe this value will be different, okay? For the good transformer, this one will be very large, and this M is also large, okay? That makes good transformer, right? But just to forget about the transformer model now. This is just purely mathematical business, okay? So first you need to measure L1, L2, and M. L1, L2, they are very easy to measure. Just to measure inductor here, leaving the other winding open, and to measure inductance here using some LCR mirror or the impedance analyzer. Then L2 is measured directly, and one is you need to measure this M. Right? There are simple trick to measure this M. You make 2 different connections. Okay. So from here, from this structure, you made a connection in this manner. This is okay. So this is connected to here, and this is connected to here, like this. That is called additive connection. There's additive connection, all right? Because with this connection, this L1 is entering through this dotted terminal, and L2 is, I1 is entering this dotted terminal here, and I2 is also entering this dotted terminal. Then magnetic field will be additive. That is called additive connection. It's not a series connection. It's different. Okay. It is some connection which makes the magnetic flux generated two windings to be additive. Okay. Don't use the term series connection. It's different. Okay. That's not a series connection. Additive connection. Another connection is this one. So it goes like this. Then flux generated by this winding and the flux generated this winding, they are subtractive, right? Because one winding current is entering through dotted terminal and the other winding current is leaving from the dotted terminal. This is called subtractive connection, not parallel connection. Subtractive connection. Okay. Then use that equation of coupled windings, coupled inductance. So here I1 and I2 are the same, okay, in the magnitude and in the direction. So you have this and this equation. This is the voltage generated this one, and this is another voltage generated from this winding, and they are additive. So you just add them, okay? And this one is same as this. Then this one is same as this one. This one. Then you have this, all right? So if you measure inductance of this connection from here, what you are measuring is this one. And in this connection, this is a subtractive connection, and I1 and I2, they are opposite in direction, same in the magnitude. So you have this condition, and this is the voltage developed by this winding, and this one is the voltage developed by the other winding, but they are in opposite direction. So you have negative sign here, and this one is direction is opposite, so this is opposite. Then you have this, right? So inductance measuring with this connection is just this one. So you made two measurements and use this equation. You already know this LS, no. This one is M and L1 and L2 are measured. So you know all the parameters of the coupled inductor model. Right? The other step is you just play with this model. This is original, this model, and convert these things into this T equivalent model. So this is the T equivalent model. Then you place this value here, this value here, this value here, and set up the lubrication for this loop, and set up lubrication, this one, relating I1 and V1. And I2 and V2 is the equation. This is the same as the original equation. Right? So they are equivalent circuit models. Okay? Then another modification. I don't know how people come up with this. Somehow use this. Okay, so this can be modified to this. This A can be any number, any arbitrary number. Okay. Other than 0. 0 is some problem. Other than 0, any number is okay. So A is an arbitrary number, and you set up KCL here and another KCL through this path, right? So this is the equation of this one. It simplifies to this by this cancellation, and this another KCL equation, which one is this, it simplifies to this one. So they are same thing. Okay. So now you select this A smartly to simplify this. So you select A as this number. If A is selected as this number, then this one becomes this, and this value is always positive because of the equation. Otherwise, you are in trouble. You have minus L. You don't know how to implement the minus L. Right? So this number becomes positive, and this K is K is this one. So we have K squared here, so K is this one. This is called the coupling coefficient that efficient reflect the closeness of two windings. So if K is closer to the unity, then you have very tight coupling in between two windings. So coupling coefficient, and this one becomes 0. Okay, so you eliminate this one, and this one it becomes this, and this is always positive. So you have something squared here. This is always positive. So then you have this, and this. Okay, so this A is selected like this. L2 divided by N. This number is different from unity. Okay, you can see that from the expression. So you have this model. So one inductor is here, another one is here, and we have 1 to A as the turns ratio of ideal transformer. Now this becomes ideal transformer, and this can be considered as the leakage inductance of practical transformer, and this is a magnetizing inductance of practical transformer, and this part is the simplified or ideal transformer representation of practical transformer. Okay, so this may model the practical transformer. Okay. So you have some strange structure like the low profile transformer. This will be large, will be small, something like that. So if you have this coupled PCB winding, this value will be different from the conventional transformer. Still the model works. Right? Because we start out from the very general coupled inductor model, which can model any two-port network, right? But we come up with this number. So if we know this number, then we can analyze the circuit like we have some strange transformer in between, right? So we measured these three parameters, okay? So we measured three parameters and translated them into this one, LK, LM, leakage inductance, magnetizing inductance, and the turns ratio of ideal transformer, and this R1, R2. We just measured this using the multimeter, so just ohm meter. It can be easily measured, winding, but this is the DC resistance. Later on, we will move to the higher frequency. The AC resistance will be way different from this one, but somehow we measured this. So look at this number. This is different from the one, and this LK is large, and LM is small. So ratio between it just 30 times, something like that. All right. So this is our model of coupled PC winding, modeled as some strange transformer, okay, maybe large transformer, and this shows the accuracy of the model. This is the simulation curve of two different setups. One is we measured this. This is our PCB windings. Physically, we applied this AC voltage here and measured the magnitude of AC voltage. This is the DC voltage gain curve with some scale factor, or this is the ratio of sinusoidal input or sinusoidal output, or ratio of DC in, DC out. Okay, so we apply the sinusoidal wave and measure the magnitude of them. Is this one, and this is the simple PSPI simulation. Here we just used this reactive component, assuming this R1 and R2 is 0. But in hardware, we have some value of R here, this R. Okay, this R we varied based on this frequency because of the skin effect. Right? Somehow we simulate this and measure this hardware. So in here, we assume this R1 and R2 is 0, but in hardware, we cannot eliminate this winding resistance. So this will be different from 0 and maybe different from the DC resistance. Somehow, because of that, maybe there is some error in between here, but this is okay. Okay, we have maybe 20% maximum error in measurement and the simulation. Okay, this might be okay. And sinusoidal analysis. Sinusoidal analysis. For that, we need to have this RE. Okay, we have R, L here, but we are seeing RE here. But we already know this. This RE is RL. Multiply by 8 divided pi squared. So let me once more go through the details about this. This is not a difficult problem, but somehow in the past I was worrying about these things. Okay. The idea is very simple. We are trying to find the ratio of magnitude of this VR1 and IR1. Okay. So the relationship between IR1 and the IO is this one. Because RR is the sinusoidal waveforms is rectified here, and average value of this becomes IO. AC component is entirely passing through this capacitor. So we have this relationship. It's not a VO, it's IO. Okay. Then we have this relationship. IR1 magnitude is, we have expression here. IO appears here. Right. The other one is this Fourier is actually there is square waveforms like this, and this the peak value is VO, and this bottom value is minus VO. We have Fourier series expansion here, and the relationship between VR1 and VO is this one, and ratio is just ratio of this one and this one. Okay, so this becomes 8 divided by pi squared, and this are L, which is this. Right? So actually, this number is very close to 1. This is 1.2 or 0.8. Either of them, you may assume this is 1. Okay, it really doesn't matter. Right? And DC conversion ratio, you went through this. Okay. If we use the simplified model, I presented the simplified model. And when I was preparing this originally, maybe 10 years ago, I followed the Erickson's approach. So I need everything. But later on, everything cancels out. Right? Or you directly related the magnitude of this, so on. Right? So you skip all this procedure, and the remaining part is this one. Okay? AC response of this tank circuit. And we have factor of 0.5 because this is half bridge, right? So here we have half bridge circuit. So 0.5 is coming from the half bridge, and we know this is 1 over RE is pi squared divided by 8. Then that cancels with everything. So everything cancels. So the remaining is this one. RL is also cancelled. RL is here. Right? RL is in the bottom. Everything cancelled. Right? So you have 0.5 here, and this is the magnitude of the tank response evaluated at the switching frequency. You just put J omega S here. Okay? Then you have the gain curve, which represent the DC in, DC out gain, DC gain with 0.5 in front because of the structure of half bridge circuit. So this is the equation, right? Qualitative analysis of this one. This is the exact equation, but I prefer to use some simplified equation using the asymptotic behavior, right? This is the model for the tank circuit, which is this, and I deflect this one to here. So RD prime is appearing here, but this transformer remained here, right? We just transferred this to primary side, but this transformer is still there. So you have 1 to A transformer with output circuit open, right? So this is the circuit we're going to use, right? At the resonant frequency, if this CR resonant with LK, then this is shorted, then voltage gain from here to there is just 0.5. No, just A. So A, okay? You have A, And when RE prime, this one is very large, very small, we have shorted, then you have this structure. This is the equation for that case. This is shorted, right? No. Oh, no. This becomes very small. Then Rm is disappearing. So Rm is disappeared. This is the voltage gain for this. And this is what? Bandpass filter characteristics. Because we have initially differentiation with +1 slope. We have double pole at the resonant frequency. And it goes to the -1 slope. We have double pole. Okay? Then this like this. So this peak gain at this resonant frequency is simply A. So this is bandpass filter characteristics. Right? If Q increase, this peak remain the same. Only this width it becomes narrow. So maybe you have this type of diagram. Right? It does not go beyond this level because the maximum gain is always A here. Okay, it won't change. The other part is assume this RE prime is very large. So RE prime is very large. So parallel combination of this one simply becomes L1. Okay, so assume RE prime is infinity. So you have this circuit diagram of this and transfer function. So this has this one. At low frequencies, you have double zero. So slope is increasing by 40 dB per decade plus 2 slope. And we have double pole here. This plus 2 slope becomes 0 slope, horizontal line. And this high frequency value is just the ratio of this inductive parameters multiplied by turns ratio of the ideal transformer, which is this. Okay. Q now is infinity. So it peaks to the infinity. Like this. Just combine those two curves smoothly, then you have this curve. Okay? This is the voltage gain curve, DC in, DC out voltage gain curve, or the AC gain curve of tank circuit. They are same thing. And this value, we have A, but we have a factor of 0.5 because of half-bridge structure. So this value is A divided by 2, and it slightly declines, and at high frequency, it converges to this value. And at low frequency, it picks up like this. It starts from the very small RE. It goes this direction as RE increases to infinity. This is our prediction based on the asymptotic analysis of transfer gain expression, and this is the simulation result. Okay, this is simulation result. With very small RE, you have these characteristics. I increase RE, I don't know, it's not infinity, maybe very large value like 10 kilo ohm, then it picks up. Right? So later on, we select the operational region. In the previous lecture, we conclude that the desired region is somewhere here. Right? The reason avoiding this region is because this gain becomes almost flat. This means to change gain, voltage gain, this switching frequency should change a lot in this region. In this region, switching frequency changes small, voltage gain changes this much. But in this region, frequency range changes this, voltage gain change only this much. Okay? So this is another good region to operate. But somehow the structure of the PCB windings, okay, and some requirement of our voltage regulation, actually we selected the spec, but we don't want to change our spec. Okay? So operational region is selected like this. That implies the switching frequency should change this much. Maybe 5 kilohertz to 1.5 megahertz, which is huge. Right? But that is that we find out this finally. So we didn't modify our design. We kept on going to our goal. This is very important. I was surprised some of students, they are not familiar with this kind of concept. This is the voltage gain curve with different values of R. R 10 ohm, 12 ohm, 15 ohm. Okay. Depending on the R, this gain characteristic changing. Right? So R is changing this much. Then we should consider this one and this one. At least two curves are necessary. Okay. And this in voltage is varying from 40 to 60 volt. And our voltage is desired to remain at constant at 24 volt. Then duty ratio at this low line is this, voltage gain at this low line is 0.4 and high line is 0.4 and low line is 0.6. So operation region is, we should select this one, this curve, and another curve. So this vertical distance takes care of this range, and this horizontal curve takes care of this variation. Right? So with this condition, let me draw this vertical line. No, horizontal line. One here, another one here. Okay. So and we have two curves depending on the load variation. One line is this one, and another line is this one. The region covered by this curve, and the two horizontal lines are what? They are the region of operation. Right? So if you change this one in this range while maintaining the out voltage 24 volt, then the switching frequency should be somewhere here. So it varies from this 670 kilohertz to 1.7 megahertz. This is a huge variation in switching frequency. So this is not a good design. One smart guy will limit somewhere here like this. Then he needs the different design of this PCB windings. Right? But with the given PCB windings, this is our best approach. Okay. So this is the range of the switching frequency. It should change from this one to that one, 1.6 megahertz. Okay, this one was okay. We did the MOSFET. We selected. We didn't have any major problem in drive circuit. And this frequency is F infinity is this one. This is the F0 is this one. Right. This is the curve. Okay. And this is the gain curve. Just to simulate using that simplified model, and this is the point. This point is we measured using that converter. We built that whole converter and measured. Okay, this one is just the PCB winding. This should be AC. We applied the AC. We measured the AC. Okay, AC in, AC out. Then that ratio of magnitude of input sinusoid and output sinusoid is this one, this point. So this is the case of 15 ohm, 12 ohm, 10 ohm. So maybe we have some difference between this. This comes from the R. We didn't consider R in simulation. So this comes from the R, and the combined effect of the skin effect of this copper trace. Okay, but trend is okay. So this might be okay, right? So we saw this. So maybe this is reasonable, right? Even you have some deviation here. The closure control of converter will take care of that differences. Okay, it really doesn't matter. Maybe the switching frequency will be slightly off our predictions, but it's okay. Okay, so. I don't remember how to measure this. They are the same thing. Basically, they are the same. Maybe the whole converter, using the whole converter, we apply this and measure the DC voltage, or just the PCB windings and the filter, tank network, we use AC waveforms. I don't remember. Okay. Maybe we use the DC voltage source. So this is also good result, right? Input impedance analysis. Because we are measuring input impedance from the primary side of transformer, it's better reflect this one to this side, right? So with this, you have this, okay? And R, the critical prime, okay? R critical seen by this side is this one, and R critical seen by this side is this squared, N squared, okay? So this is, they are same thing, just you have this, the scaling factor, and this is F0, F infinity. This one is F infinity, not F0. Oh. This should be F infinity, and you have F0 and Fm. So this is our prediction based on our previous result. Okay, GI infinity, GI 0, R is increasing, and R is increasing. Then magnitude of GI increasing, so you have a good line of efficiency. This right-hand side of this vertical line, we have poor line of efficiency, and the left-hand side of this equation, and this are critical. With this and above this value is value of the R, D prime or RL. Okay, so it really doesn't matter. Just we need to change the scaling factor, and above this line you have GBS, and below that line we'll have GCS. Okay, so I compared this one. Oh, okay, I use the DC source and the DC output. This is the converter, including everything. So I use the DC in, DC out to confirm the validity of this curve. And here, I used this AC voltage. So this is long. It should be AC, right? AC in, AC out. Okay, AC voltage in, AC current out. Right? And this is the input impedance curve. So I overplot the operational region on this curve. This is possible because we know the range of switching frequency here. So always this axis is frequency. So with that information, I can specify this like this. This is operational region for our converter. So this region might be okay, but this region is bad because with this, the switching frequency is changing widely like this, right? And for the simulation, I use this. This is a simulation curve. For the measurement, I used this, okay, this, and we measured the magnitude of this AC voltage and recorded the magnitude of this AC current, okay, and ratio of between this number is a GI magnitude, and GI magnitude is put here as a triangle point or circle point and rectangular point. Right? Again, you have some difference. Probably the presence of this resistance, winding resistance, which changes as the function of switching frequency due to the skin effect. So this error as expected, right? But error bound is observable. We analyze everything. So this is the overplot of operational region on the input impedance curve. So you have 4 corners defined here. So you are using the same corner. This is operational region specified on this input impedance curve here. So is point A, point B, point C, point D. Okay. This is the range of switching frequency change. It varies from this value to this value, right? And at this point, there's a point X. Switching frequency was 1 megahertz. We measured this input impedance, and we measured the waveforms. So this tank voltage is this one. This tank voltage is this, right? So this is 0. 0 line is here. Peak value is Vs divided by 2. Bottom value is minus Vs divided by 2. And this is tank current. So tank current start from value less than 0, negative value. That means during this period of time, D1, body diode of upper switch is conducting. And later on, this channel is created, but after some time, the channel is delivering this current with 0 voltage condition because the body diode is already conducting. So this confirms the GBS operation for the upper switch and the GBS operation of lower switch. So this might be good. And this peak value is recorded. I read this scale about the 4.7 M of the operational condition of this. All right. So maybe it is interesting to this value from the prediction of this tank impedance. Right. So at this frequency, switching frequency was 1 megahertz, and the RL is 10 ohm. Then the our voltage was 24 volt, and the voltage gain is 0.5. That information is shown in this curve. This curve, okay. So 1 megahertz here, switching frequency, voltage gain is about 0.5. Okay. So with that condition, we can predict the value of input voltage indirectly, right? So from this information, we predicted Vs, and the magnitude of GI was this one. Then IT1, fundamental component of tank current, seen at the input port, as this one, which is 4.7 volt. Okay, so this one is very close to this. Somehow this prediction of this fundamental frequency model, everything is in every analysis here, we assume, implicitly assume that the voltage waveform, current waveform are purely sinusoidal. That's called the sinusoidal approximation. Okay. Initially we assume that, and all the analysis design people, everybody is assuming everything is sinusoidal. That is the fundamental approximation. Without that approximation, it's extremely complicated to predict anything about this. Okay? So this is good, right? All right, so maybe we stop here. And tomorrow we'll finish up the remaining part of this analysis. Except one thing. We don't touch anything about the compensation design now. Okay? So we are using that stupid integrator structure with some value. Okay? Trial and error method was used to select that to maintain the stability and the DC regulation. Okay? So there is no information about the transient response of this thing at all. Right? So we complete this story in this manner. And after finishing this, we go back to the beginning and talking about the dynamics and the control of this resonant converter, okay, which is very, very challenging task. Right? Okay, we stop here. Thank you.